A black hole 50 million times the mass of our Sun was found fully formed just 700 million years after the Big Bang, and it outweighs every star in its host galaxy by a factor of 6, which should be physically impossible under every model we had. Scattered across JWST's deepest images are hundreds of tiny crimson specks the size of a pixel. Objects so strange they have forced a complete rethink of how the universe built itself. The strangest of all, a triply lensed object called Abell 2744-QS01 became the first black hole in the infant universe to have its mass measured directly. What astronomers found inside upended a 50-year-old assumption about cosmic order. This is the story of what JWST found, why it matters, and what it means for everything we thought we knew about how galaxies are born. Here is the number that rewrote the rulebook: 50 million. That is how many times heavier than our Sun this black hole is, sitting at the center of a galaxy so underdeveloped that the black hole itself accounts for roughly 2/3 of the entire system's mass. Not 2/3 of the central region. 2/3 of everything. Every star, every cloud of gas, every wisp of dust, outweighed by a single object at the core. In any galaxy we see today, the black hole makes up about 0.1% of total stellar mass. Here, it is the dominant structure. The galaxy is an afterthought. That single measurement, announced in May 2026 in back-to-back papers in Nature and the monthly notices of the Royal Astronomical Society, delivered the most direct answer yet to one of cosmology's oldest questions. Which came first, the black hole or the galaxy? The answer, for this object at least, is unambiguous. The object has a nickname that undersells it dramatically. Little red dots are compact crimson specks that started appearing in JWST images from the moment the telescope began returning data in 2022. They are extraordinarily common in the infant universe, clustering in the first 1 to 2 billion years after the Big Bang, then vanishing almost entirely by the time the cosmos turns 1.5 billion years old. No telescope before JWST could see them at all. Their extreme redness initially tripped up astronomers, because light from very distant objects stretches toward red wavelengths as the universe expands. But these objects were red even after correcting for that effect, suggesting something unusual was happening inside. Most astronomers now believe each little red dot harbors a growing supermassive black hole wrapped in a thick, dense cocoon of gas so opaque it blocks nearly all conventional radiation. That cocoon is exactly why they are so hard to classify, and exactly why one particular lensed example changed the entire conversation. Abell 2744-QS01, designated QS01, sits behind Pandora's cluster, a massive galaxy cluster called Abell 2744. That cluster acts as a natural gravitational lens, bending and amplifying the light from QS01 so powerfully that the object appears 3 separate times in a single JWST image. The lensing magnifies QS01's brightness by a factor of 6 and stretches it spatially by a factor of 3.5, giving astronomers access to detail that would otherwise be invisible. A second lensed little red dot, Glimpse 7775, sits behind the cluster Abell S-63. JWST spent 30 hours collecting its spectrum, but gravitational lensing made that exposure equivalent to 80 hours of observation time, producing the deepest spectrum ever taken of any little red dot. More than 40 individual spectral lines emerged from that single observation, all pointing toward the same answer. Nature handed astronomers a telescope upgrade they could not have built themselves, and they used it to read the gas around these black holes, like a fingerprint. Measuring a black hole's mass directly, without assumptions, is one of astronomy's hardest problems. For QS01, the team used spectroastrometry, tracking tiny positional shifts in the light emitted by gas at different wavelengths as it orbits the central object. The gas motion revealed something unambiguous: pure Keplerian rotation, the same mathematical signature that describes planets orbiting the Sun, but centered on a point mass of 50 million solar masses. Keplerian rotation only occurs when most of a system's mass is concentrated at a single point. If there were a substantial population of stars distributed throughout the galaxy, the rotation curve would look completely different. It did not. The upper limit on the total stellar mass of the galaxy hosting QS01 came out below 20 million solar masses. The black hole is heavier than all the stars it supposedly grew from. That is not supposed to be possible under the standard model of galaxy formation, where black holes feed on matter supplied by an already established stellar system. The chemistry of QS01 tells an even more radical story than its mass ratio. The gas surrounding this black hole is overwhelmingly hydrogen and helium, the two lightest elements forged in the Big Bang itself, with almost none of the heavier elements like carbon, oxygen, or iron that stars produce when they live and die. In astronomy, metallicity is a clock. Stars forge heavy elements and scatter them when they explode. A galaxy rich in those elements has processed many generations of stellar birth and death. A galaxy poor in them is either extremely young or has had very few stars. QS01 is chemically pristine. Its environment looks like the universe before stars had time to do meaningful work. Roberto Maiolino of the University of Cambridge called this finding a paradigm shift, a total revisiting of the classical scenarios of how black holes form and grow. The implication is stark. This black hole did not wait for stars to build a galaxy around it. It arrived first, and the galaxy is only just beginning to assemble. Standard cosmology says supermassive black holes grow from stellar mass seeds, the collapsed cores of massive stars, which then merge and accrete gas over billions of years. But QS01 masses 50 million suns in a galaxy that barely exists, 700 million years after the Big Bang. The math does not work by that route. Several competing formation paths are now under serious investigation. One proposal involves direct collapse black holes, primordial gas clouds that bypassed the star formation stage entirely and collapsed straight into a massive black hole, skipping millions of years of stellar evolution. Another model points to super Eddington accretion bursts, where a smaller black hole swallows gas at rates far beyond the theoretical limit for brief, violent episodes, growing at speeds once considered physically impossible. A third line of evidence from a January 2026 Nature study found that previous mass estimates for little red dots were inflated by up to a factor of 100 because their thick gas cocoons scatter light in ways that mimic a much heavier system. Corrected masses fall between 100,000 and 10 million solar masses, comfortably within reach of more exotic formation channels, but still far ahead of any surrounding stellar population. Every cosmological simulation ever built assumed the same sequence. Gravity gathers gas, gas forms stars, stars build galaxies, and somewhere in the middle, black holes grow. QS01 breaks that sequence at the first step. If black holes can precede galaxies, then the structures we see today, the Milky Way, Andromeda, every spiral and elliptical in the observable universe, may have been organized not by star formation, but by the gravitational anchor of a pre-existing black hole acting as the seed around which everything else assembled. That is a fundamental inversion of cosmic architecture. JWST is now targeting other gravitationally lensed little red dots to test whether QS01 is an outlier or the rule. If the next confirmed case shows the same pristine chemistry and the same overmassive black hole, the standard model of galaxy formation will need a structural revision. The question is no longer whether black holes can come first. The question is whether they always did.